In this session, ladies and gentlemen, we're going to learn about integration. So, integration can be simply regarded as the reverse of differentiation. Integration is the procedure of finding the area under a curve over a function. We can as well say that integration can be used to identify the specific revenue and cost functions given their marginal functions, as we shall see as we get deeper. I want us to learn a simplified process of integration. But before then, shall we either understand a notation and rule for integration? Either way can be defined as indefinite integral. So the integral of a function, for example, n raised to power n, will be given by x raised to power n plus 1, that a particular value divided by n plus 1, then you add a constant, whereby this constant, we're saying it is a constant based on the value or the function that you are integrating. Look at these particular examples given below. Then keenly allow me to move to the next part where I'm going to give a simplified process, elaborate what is happening in these particular formulas. So in order for us to learn comfortably how to do integration, ladies and gentlemen, allow me to borrow from the introduction of integration where we've said it is the reverse of differentiation. Then I'm going to start from elaborating the steps we learned in differentiation so that we analyze how to do a reverse of those steps, because they shall give us the simplified process of doing integration. In the process of learning differentiation, we are saying that the first step is multiply the power with the base. Then secondly, you less 1 from the power. So that means if we had to do the reverse of this particular process of differentiation, our last step becomes the first now. So the part of we less 1 from the power becomes our first step, but we do the reverse. Therefore, the first step in integrating will be add 1 to the power. The second step, what came after lessing in differentiation, was to multiply power with base. Therefore, we do the reverse. So our second step in integration becomes divide the base with the new power. Remember, this power we've just added 1. So divide base with new power. Then the final step is you say plus a constant, because maybe there was a value during differentiation that was cancelled to be 0. Because we don't know the exact value how it could be, in integration we'll always say add a constant after we've finished integrating all the elements in the function given. A clear example, let's integrate function where we've been given that y is equals to 24x squared minus 3x raised to power 5 plus 9. Of course, we are following the steps in integrating. That is, add 1 to the power, divide the base with the new power, then add a constant. Let's go. First step, add 1 to the power in the various specific segments in the function. Start with the first one. 24x squared. The power is 2. The base is 24. So adding 1 to the power, now x becomes raised to power 3 because of 2 plus 1. Divide base with new power. Our base is 24. Our new power is 3. 24 divided by 3 is 8. So that segment we shall have 8x cubed. Less. The next segment is of 3x power 5. Add 1 to the power. The power is 5. 5 plus 1 is 6. Second step, divide base with a new power. So 3 divided by 6, the new power, is 0.5 or half. So that segment we shall have 0.5x raised to power 6 plus. The other section is 9. 9, there is an assumption as x raised to power 0. So the first step of add 1 to the power. 0 plus 1, we get 1. Divide base with new power. 9 divided by 1 is 9. Therefore, that section we shall have 9x. Then, like we said, after integrating all the sections in the function, you say plus a constant. If you had checked the function we've done before on differentiation, you'll realize the function we've just achieved after differentiating, after integrating 4x squared minus 3x power 5 plus 9 is the function that we had when we were differentiating. Let's simply know the integral function of 24x squared minus 3x power 5 plus 9 will be 8x cubed less 0.5 x power 6 plus 9x plus a constant. Try to do several examples because after this we go directly to the application. Application of integration. We are constantly borrowing from differentiation. Differentiation, we had said, will be used in obtaining marginal revenue from the total revenue. And because integration is the reverse of differentiation, therefore, we can comfortably say you integrate the marginal revenue to obtain the total revenue function. Similarly, you integrate the marginal cost to obtain the total cost function. As simple as that. Let's look at this particular illustration. It tells us that your company manufactures large-scale units. It has been shown that the marginal or variable cost, which is the gradient of the total cost curve, is 92 minus 2x. This is the amount of shillings in thousands, where x is the number of units of output per annum. The fixed costs are 800,000 per annum. It has also shown that the marginal revenue, which is the gradient of total revenue, is 112 minus 2x, again in shillings in terms of thousands. Then are called upon to determine total cost function, total revenue function, quantity sold at break-even point, quantity produced to maximize profits, and the maximum profits realized. Let's look at the solution of the first one, that is determining the total cost curve. First, we realize that we need to determine the indefinite integral limit of the marginal costs as the first step to obtaining the total curve. You remember the steps? We get the function, add 1 to the powers, then dividing the base with the new powers, then we add a constant to the function. So let's go. The marginal cost function is 92 minus 2x. We get the indefinite integral limit will be given by 92x minus x squared. Then, of course, plus a constant. We know very well that in total cost function, the constant part is the fixed costs. So the constant term in the integral will be representing these fixed costs. According to the elaboration, we have been told that the fixed costs are 800,000. And since because our functions are given terms of 1,000 shillings, we are going to have the constant value being 800. Therefore, our total cost function will be 92x minus x squared plus 800. We can rearrange the same function and have 800 plus 92x minus x squared. Going forward, ladies and gentlemen, we have either been tasked in determining the total revenue function. So as in the above case, the first step in determining this total revenue is to form the indefinite integral of the marginal revenue. The same steps we did, we will follow the same again here. Our marginal revenue function is 112 minus 2x. Therefore, integrating the same using the steps we have named above, we shall get 112x minus x squared, and of course, plus a constant. In this case, we realize that in total revenue, 0 units sold means 0 revenue. Therefore, the constant is always a 0 if there is no function done. And for that reason, our C will be a 0. Therefore, we shall retain our function as total revenue being 112x minus x squared. Moreover, we have been tasked in determining the number of units to be produced at break-even point. Borrow the understanding from economics where we have been saying that at break-even point, the total revenue is equal to the total costs. Therefore, from the two functions obtained above of total revenue and of total cost, we simply equate them. We know that the total revenue is 112x minus x squared. Therefore, we equate it to the total cost function, which is 800 plus 92x less x squared. Mathematically working on this one, by grouping like terms together, at a point we shall get 20x being equal to 800. Divide both sides by 20, we will get one side having x is equal to 40. Therefore, 40 will be the number of units to be produced by the entity for it to achieve the break-even point. with some other items to work on, ladies and gentlemen. Allow me to give that as a personal assessment again, Adam, for you try to see if you're able to determine the quantity that the entity should sell in order to maximize profits, because we did it when we are analyzing differentiation. Again, go ahead and determine the particular maximum profits that can be realized by the entity. Allow me to go to another process of doing integration, whereby you have been given in terms of a task to work out the area under a particular curve. Like, for example, you have been told to integrate the function of 6x cubed plus 2x plus 3. Area covered will be under 12 and 5. So in this case, it is the easiest. You simply substitute the x by the discrete values given, obtain the summation of the two impacts independently, then determine the difference between the two. Like, for example, if we first start by substituting x by the bigger value, that is 12, and where we got x, I will place 12. Therefore, my equation now becomes 6 times 12 raised to power 3 plus 2 multiplied by 12 plus 3. That gives me 10,368 plus 24 plus 3. Summation of that part ultimately gives me 10,395. I move to the other section. I replace again with value 5. Therefore, my equation now becomes 6 times 5 raised to power 3 plus 2 times 5 plus 3, giving me 125 plus 10 plus 3, sequentially giving me 763. I determine to get the difference between the two. 10,395 minus 763. Ultimately, I will end up getting 9,632. 9632. Therefore becomes the area under curve of 12 to 5 of the function of 6x cubed plus 2x plus 3. Thank you, ladies and gentlemen, for the participation in today's presentation on integration. Of course, it has been prepared and presented by myself, Patterson. Wish that you are going to subscribe and follow my channel as we get deep and better in dissecting quantitative analysis and other business mathematics and statistics problems. For Shizu.